Hello, ladies and gentlemen. Today we are going to discuss geometric probability. For your notes today, you're definitely going to need a calculator, of course, writing some notes in there and something to write with. So let's think about what we already know about probability in general. That is the chances or the likelihood that something's going to happen. For example, the probability of drawing a king out of a deck of cards. You would be thinking to yourself, well, there's 4 kings out of 52 total cards, so that would give me a probability of 4 out of 52, and I could divide that to convert that to a percent. The probability of a fire drill during this class. Well, how many minutes is this class out of how many minutes in the school day? And we would divide that to find a percentage. The probability of rolling a number divisible by 3 on a die. So how many numbers are divisible by 3? And then how many numbers total could be possible to roll? This idea of probability is a huge one, and now this ties into geometry when we talk about geometric probability. We're talking about geometric shapes and finding the probability of landing in a certain region. Oftentimes, many games rely on this as their fundamental principle. Pin the tail on the donkey. Carnival games where you have to toss a ball into a little jar, or toss a coin over there, or put a ring on a bottle to win that prize. All of those deal with geometric probability. So let's define what probability is. It's the favorable outcome. In our case, it's a region. So where do we want to land, or what are we wanting to have happen, or what are we finding the probability of over the total region, all possible. So in our case, that would be total area. Now, oftentimes this could be written as the fraction, reduced, of course, or you'll see it written as a percent. Oftentimes people will discuss them in terms of percentages so that you can kind of gauge how likely it is that something would happen. So let's consider this example first before you write any in your notes. A point is chosen at random along this segment. Find the probability that the point is on AB, and then the other situation, BD. So let's first consider how long AB is. How long is the distance between A and B? Well, that's 2 units, right? 1, 2. You can see that from the 0 to 2 distance, right? And the whole segment has a length of 18. So the probability of me dragging a point somewhere along here and just saying stop and landing in the region from A to B, well, that'd be 2 out of 18, which is 1 out of 9. But then, as I said before, more likely people like to hear that written as a percent. So if you divide 1 divided by 9, you get 0.11 repeating, which would be 11%. Okay? So let's talk about BD. B to D, how long is that? Look at that. That's 2, whoops, let's go back. That's 2 to 11. So that would be a distance of 9. And then over the whole distance, 18. So 9 out of 18 is 1 out of 2, or again, 50%. So the chance or the probability of landing from B to D, if I were just going to grab a random point along here, would be a 50-50 shot, really, a 50% probability that that would happen, because that's half of the distance of the segment. Let's take a look at another example here. Got some writing on there. I think I should erase. There we go. We'll just scribble it out here. There we go. Finally erased. So let's take a look at this one. We have a trapezoid, and we're going to find the probability that the spot is in the blue regions. So we're going to basically have a random point on here. We're going to choose what's the probability that it would land in the blue regions and not in the white one, okay? So let's first consider the area of the blue regions, because we're going to need to figure out that area over the area of the total. This is our setup. So let's find the area of the blue regions here. Well, we'd have one little triangle here that is 4 by 4, and triangle area is base times height divided by 2. So this would have an area of 8. Now on the other side, what's this triangle? Is that another 4 by 4? Well, the height would be here. But is this length 4? Well, let's figure that out. I have 16 all the way across, 4 to right here. That leaves me with 12 minus 7 more, so this has to be 5. 5 plus 7 plus 4 makes 16. So this area over here is 5 by 4, which is 20, but remember it's a triangle, so 20 divided by 2, 10. So that has an area of 10. So the blue area is 18. Now we need to find the total area. The total area, if I read this as a trapezoid, you can again do the trapezoid formula. the total area, blue and white combined, is 1/2 the height, base 1 plus base 2. 1/2, the height of the trapezoid was 4. And then base 1 is 7 plus base 2 is 16. So if I start in the parentheses there, I'd have 7 times 16 is 23. So I have 1/2 times 4 as well. That'd be 2. So I have 2 times 23 is 46. So the total area is 46. Now to find that probability, yeah, 18 out of 46, we could reduce that. But like oftentimes, again, it's about that percentage. So we would just take 18 divided by 46, expecting to get, a decimal value. We get 39.3913, which is approximately 39%. Move that decimal point over 2, and that's your percentage. So this is what we're going to be using, that idea of area and different figures and probability, sort of to bring it all together here. This is the one I need you to get into your notes. It's a picture of a carnival board, okay? So this is a big, wooden cutout. It's standing upright, and you toss a bean bag in the general direction of this, hoping that you're talented enough to land it in one of those regions, right? If we blindfolded you and just had you randomly throw it at the board, what's the probability that we're going to get it in the beanbag in the nose, or get a beanbag in the eyes, or just winning a prize in general? So take a minute and copy down the picture, and on the side put the probability of a beanbag in the nose, beanbag in the eyes, and winning a prize, and then we're going to calculate those. Okay, so now that you have that drawn into your notes, let's find the probability of landing a beanbag in the nose. So the nose is right here, right? The nose is a triangle shape. So that area is 1/2 base times height. So if I take 18 times 5 and then 18 times 15 and then divide that by 2. So in essence, you're taking 9 times 15 here. We would get 135 centimeters squared. So I know the area of where I would like to toss the beanbag is 135 centimeters squared. And the area of the whole region, 140 times 90, remember that's one big rectangle here, is 12,600 square centimeters. So if I take 135 divided by 12,600, let's see, we get 0.0107. And if I move that decimal place over 2, I get about 1%. That's a pretty small chance of landing into that beanbag nose, or into the nose with a beanbag there. Okay, let's talk about the eyes. Now there's 2 of those, so we would expect our probability would be quite a bit more here. We have 15 by 20 for one of them, so 15 by 20, if we go ahead and calculate the area of that, would be 300. Now remember, there's 2, one here, each is 300. I'm just going to jot that down in here. So the probability of the beanbag in the eyes would be 600 out of the total. Again, we don't have to refigure that out. That's still the same. So we'd end up with 600 divided by 12,600. And if we calculate that in our calculator, we get 0.047. So if I move the decimal point over 2, I get 4.7%. You would probably round that up to 5, but that's approximately the percent chance of that happening. So what's the probability of winning a prize in general? So assuming we have to get a prize here in one of these little openings, toss a beanbag in the open spaces to win a prize, like the setup says up there, we're going to need to find all the regions here that win us a prize. So we have to deal with these little circles down here yet. So the circles have a radius of 6, so each one would have an area of 36 pi, pi r squared. 36 pi times 1, 2, 3, 4, 5. So if I have 36 times 5, I have 180 pi for all of these circle regions added together. So 180 times pi, or times 3.14, is like 565-ish, okay, for those circle regions. And now if we add all of these together, all of the regions that earn us a prize here. So I'm going to add in 600 for the rectangles above, and add in the 135 we want to find that total 565.2 plus 135 plus 600. We end up having 1,300 approximately 0.2 for all the areas that win us a prize over the 12,600. So if we divide that by 12,600, because that's the total, that will give our probability of winning the prize, and that is 0.103 or approximately 10%. So the chance or the probability of winning a prize, if I'm doing this at random with my eyes closed and throwing it towards the board, only a 10% chance of winning anything at all, okay? So I want you to think about probability as we move forward and how using that area helps us determine the probability or the chances of something happening. I want to thank you for taking good notes. Have a good diagram in your notes. I'll be looking for that tomorrow. Kincaid out.